Hi everyone. Today let's talk about sessions 8.3, Hamiltonian cycles and the traveling salesperson. Hamiltonian cycles are named in honor of Sir William Hamilton, who marketed a puzzle with cities connected by segments. It was actually a dodecahedron where each corner was labeled with a city name. The goal was to follow a path that will visit each city once and return to the original city. So this is the Hamilton's puzzle 3D picture. Okay, and if we draw it in two-dimensional, this is the graph. Okay, so can we find a cycle that visits each city once and return to the original city? So you can see this is a cycle. This is a cycle that visits each vertex once. Okay, so definition. If in a graph of G, there is a cycle which contains every vertex of G exactly once, except for the beginning and the ending vertex, then we say the cycle is called a Hamiltonian cycle. And there are no verified, necessary, and sufficient conditions known for the existence of Hamiltonian cycles in a graph. Do you remember last class we talked about Euler cycle? The Euler cycles exist if and only if G is connected and all the vertices have even degrees. Okay, but here we don't have sufficient and necessary conditions for the existence of Hamiltonian cycle. So in a Hamiltonian cycle, each vertex must have a degree 2 in its path. Okay, we're not saying the vertex has a degree 2 in the graph, but in the path, it must have degree 2. For example, in the picture, N has degree 3, but you can see in the Hamiltonian cycle, the path, it has degree 2. There's only 2 edges incident to it. So far, so good, everybody? All right, let's look at some example. So let's find a Hamiltonian cycle which starts with A. Okay. So this picture, let's think about more. We know that Euler cycle visits each edge once, right? Then the Hamiltonian cycle visits each vertex once, except for the beginning and the ending vertex. Okay, except the beginning and ending vertex. Oops. Okay. Alright, and for the Euler cycle, we know that's every vertex. So every vertex has even degrees, right? Okay, even degrees in the graph. So this is degree in the graph. But for Hamiltonian cycle, we have every vertex has degree 2 in the Hamiltonian cycle. Okay, it's not degree 2 in the graph, it's degree 2 in the Hamiltonian cycle. Okay, so let's see here. Let's look at this picture. Do we have an Euler cycle? Well, let's look at this vertex. Let's look at the degree. A has 1, 2, 3, 4, degree 4. B, 1, 2, 3, 4, degree 4. C, 1, 2, 3. Oh, you can see C is odd degree. So this guy is odd degree. That's why we know there is no Euler's cycle. So far, so good, because the degree is 3. 3 is odd. No Euler cycle. Okay, but do we have a Hamiltonian cycle? In fact, this case is yes. And it's usually harder to find it. Okay, so harder to find a Hamiltonian cycle. Hamiltonian cycle. And here, a Hamiltonian cycle, we want to travel each vertex exactly once. So we can start with A, B, C, D, E, F, G, and then go back to A. So this is one Hamiltonian cycle, right? So A, B, C, D, E, F, G, A. Oh, no H. A, right? And there could be other Hamiltonian cycles, so it could be not unique. Okay, so we can go like A, let's see, D, C, E, F, G, A. Okay, this is another Hamiltonian cycle. So A, B, D, C, E, F, G, A. So far, so good, everybody? Okay, next. If a graph has vertices whose degree is 2, then the Hamiltonian cycle must include both edges at each of those vertices where the vertex has degree 2. Because, well, 2 is the minimum. For a vertex, you want to go in and you want to go out, right? So 2 is the minimum that we need. Okay, so if we have vertex has degree 2, then those 2 edges must be included in the Hamiltonian cycle. Because if you want to connect to that vertex, you must go in through one edge, go out for another edge. So those are the minimum. Okay, next. The number of edges in the Hamiltonian cycle must be equal the number of vertices in the Hamiltonian cycle. Oh, why is that? Well, you start with a vertex, and then you have an edge, vertex, edge, vertex, edge, and then you go back to the starting point, right? So then if we look at those previous, you can see the number of vertices and the number of edges are the same. So far, so good, everybody? Next, you can determine if a graph has Hamiltonian cycle by eliminating edges. Okay, let me teach you how to do it. So, example, determine whether the following graphs contains Hamiltonian cycles. If no, explain why. If yes, list a Hamiltonian cycle. Okay, first of all, well, let's label the edges. Let's call this is E1, E2, E3, E4, E5, and E6. Okay, so we have 5 vertices. A Hamiltonian cycle must have 5 edges. Okay, so there are 6 edges. We need to eliminate 1. Okay, so let me put down. So we have 5 vertices. And a Hamiltonian cycle must have the same number of edges as the number of vertices. So have 5 edges. Okay, and there are 6. So there are 6 edges. So need to eliminate 1. Okay, so how do we eliminate? First look at the vertex with degree 2. Okay, so we look at vertex with degree 2. So this is this guy, which means the edges connecting to them cannot be eliminated. So we want to keep E4, E1, E2, E3, E5, and E6. Oh, you can see we cannot eliminate any of them. Okay, so here we can't eliminate E1, E2 because it's connected to B. We cannot eliminate E3 and E4 because it's incident to the vertex D, and we cannot eliminate to E5 and E6 because they're incident to the vertex E, right? So therefore, we cannot eliminate them. And then therefore, so no Hamiltonian cycle. Okay, so far so good, everybody. Let's continue. So if we try to find the Hamiltonian cycle and realize we cannot, we come up with some contradictions, so it means we cannot find a Hamiltonian cycle. Let's continue. Next one, let's label it E1, E2, and E3, E4, E5, and E6. So far, so good, everybody. Okay, so here we have how many vertices? We still have 5 vertices. And we have 6 edges. We need to eliminate 1. Okay, so we look at vertex with degree 2. Those are E and B and C, right? So we need to keep E1, we need to keep E2, we need to keep E3, and you need to keep E5 and E6. Okay, so we keep E1, E2, E3, E5, and E6. And actually, so we can eliminate E4. Then we can get a Hamiltonian cycle. Well, that will have A, B, C, D, E, A. This is a Hamiltonian cycle. So far, so good, everybody. And because there are no parallel edges, when you denote the path, you don't need to write down the edges between them. You just need to list the vertices. So far, so good. Okay, let's continue. Let's change another color here. Okay, so here let's label it. Here we have 5 vertices, right? And we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 edges. Can we find the Hamiltonian cycles? Yes, actually, this guy also work here, right? So we can do the Hamiltonian cycle. Could be A, B, C, D, E, A, right? Or we can find otherwise. We can do A, E, B, C, D, A. This is another one. So A, E, B, C, D, A. This is another one. So there are a lot of Hamiltonian cycle in this case. All right, let's continue. Okay. All right. So next example, we want to show the following graph does not contain a Hamiltonian cycles. So here I'm gonna show you 2 methods. So 2 methods to show it does not contain a Hamiltonian cycle. The first method is, okay, so method 1. All right. First, we want to look at the vertex with degree 2. Okay, and then for the edges incident to that vertex, keep those edges. Okay, so here we have like A and C. So we keep the edges AG and AB, and we keep the edges BC and CK. Okay, so let me put down. We keep the edges AG, AB, CB, and CK. Okay, then next, because every vertex in the Hamiltonian cycle has degree 2, so let's look at the, okay, so look at vertex B. Now we keep the vertex edge AB and BC, right? So we need to eliminate the rest. So we eliminate the edge BD and BF. Okay, so keep in mind every vertex has degree 2 in the Hamiltonian cycle. Okay, now let's continue. So let's look at D. So now D. So look at D. Now D, after we eliminate BD, then now there's only 2 edges connecting D left. Okay, so we must keep it. And let's look at F. There's only 2 edges connecting F, incident to F. Now we have to keep it. So we need to keep DG, DE, and FE, and FK. Right? So far so good. Now we look at E. Well, E, because now we have 2 edges incident to E that we need to keep. So the rest we need to delete it. So now delete the, okay, so we need to eliminate EH and EJ. Okay, and also look at G. Now we already have 2 edges incident to G, so we need to delete the rest. So delete this guy, so eliminate GH and GM. Same thing here, because K, we already have 2 edges incident to K that we need to keep, so eliminate the rest. Well, eliminate KJ and KM. Well, now what happened? Now the graph is, we cannot go through the edges. So here, because all these edges are deleted, those 2 we cannot reach the vertex MLHJI. So we get a contradiction. Okay, so we can reach M, for example, so get a contradiction. Okay, so if we get a contradiction, then we say there's no Hamiltonian cycle. So this is method 1.